Here we go. So let's say that we have this problem here. So tectonic plates, large segments of the Earth's crust that move slowly, so plate tectonics. And let's suppose that one of those plates moves about 4 centimeters a year, which is about, that's typically what they are. I think it's slightly more, but I don't recall. So what distance does it move in 1 second at that speed? So this question, just a real world scenario, but it's you'll notice in chapter 1 it deals with unit conversions and stuff like that. And so I just want to do some of this basic stuff applied to something that matters. So if I have, whoops, get my pen going here. So if I have 4 centimeters per year, all right, and I want to know how far does that go in 1 second, I can convert this thing into seconds. And it's by using what I'll call fancy forms of 1. If you've had chemistry, you might recognize this railroad track kind of method for unit conversion, where you make ratios and you just flip them around to suit what you want canceled. That's the method that you learn. Later on in the next week or two, you're going to learn a better way to think about that. But for now, I'm just going to kind of lean back on what you probably experienced before. So basically, I need to get rid of uh, uh, length altogether and somehow come up, with time and get just to a distance. But uh, what distance does it move in 1 second at this speed? And so since I need to get to kilometers, I'm going to go ahead and try to find out how many meters it moves. So let's say we wanted to get at meters. And so I know that, I'm going to switch colors here, every meter has 100 centimeters in it. That'll allow me to get rid of centimeters. And I know that every 1 year, that's up in the numerator, and I got year in the denominator, that's going to have 365.25 days in it. So right off the bat, my centimeters are going to drop out, my years are going to drop out, and I'm going to have meters per day. All right, so let's keep the ball rolling here. We know that 1 day has 24 hours, and we know that 1 hour has 3,600 seconds. Well, you may not know that off the top of your head, but 60 minutes in an hour and 60 seconds in a minute, 60 times 60 is 3,600. All right, so let's see what we got here. So we have days are dropping out, hours are dropping out. I actually have meters per second. So at this point, if I wanted to multiply all the numbers in the top and divide them by the product of all the numbers in the bottom, I would have the meters per second. If I wonder what's the speed in meters per second, because centimeters per year, that's easier to swallow, isn't it? That makes sense, because I can think of 4 centimeters. You know, 1 centimeter, I think 1 inch is 2.5 centimeters. So what this means is in 1 year, these tectonic plates would move a little over an inch. Okay, about 1.5 inches per year. That is something you can imagine. But this is physics class, so we want to mess with your mind and make you think about, okay, then how many meters per second would this be? Well, 4 divided by 100 divided by 365 divided by 24 divided by 3,600. So I'm going to have an insanely small number, right, of meters per second, which is almost entirely useless in a practical sense, unless you need to know the meter per second speed. Okay, so what's the purpose of this problem? Well, it's totally impractical. All right, uh, it's a conversion problem. What if I had given you this insanely stupid number of meters per second and said, give me the centimeters per year? Then you would have seen the utility in unit conversion. Okay, so you're going to have problems that are just, can you do this technical maneuver? Okay, so I would just be straight up honest with you. This problem is here. You'll have a similar problem in your homework, the one you get graded on, and it's strictly a mechanics issue. Can you perform this mathematical maneuver? Your textbook has examples on this. I'm doing an example on this. Everybody and their dog has done unit conversions on YouTube, so there is no shortage of demonstrations of it. All right, so, and now we were asked, what distance does it move in 1 second? Well, what I can do, so if I just multiply this by 1 second, all right, then what do I get? I get seconds dropping out, and the only unit in town, where'd my highlighter go, is meters. That's it. So now I've converted centimeters per year into meters by means of converting it to meters per second, and then multiply by second, I have meters. Okay, I could have just converted the years to seconds, multiplied by second, I'd have some number of centimeters. All right, so in the end, this works out to, if you do all the math, this will, oops, I need a pen here, 1.3 times 10 to the minus 9th meters. Anybody know what 10 to the minus 9 meters is as its own unit? Nanometer. So it moves a little over 1 nanometer. All right. By the way, now I'll get that later. So that's part A. We just answered part A. Part B asked us, what is its speed in kilometers per million years? Okay, so let's think about it. This is actually a useful conversion. If you've had geology, anybody, you know, it used to be the continents used to be one big happy continent, and then, you know, they started having arguments and drifting apart from one another very, very slowly, right? And eventually they'll come back together. Okay, so someday they're gonna scooch back in and start cramming together, make some new mountains, and then eventually that'll be another breakup, and there'll be a different, you know, if you could travel time 100 million billion years from now, you would see a different continent structure on the Earth. So now we can just say, 4 centimeters per year, all right? And so again, we have our 1 meter per 100 centimeters. Notice, I want to point out something. Isn't it the case that 1 meter equals 100 centimeters? Just a little side note here. So if you're taking notes, put it off on the side. And if I divide both of these sides by, say, 1 meter, isn't it the case that I just made a really fancy form of 1 there? If I multiply 100 meters per 1 meter, isn't that just 1? 100 centimeters per 1 meter? Aren't those the same length? So this much of this over this much of that, they end up being a 1-to-1 relationship. There's no leftovers. It's a fancy form of 1. And what do you get when you multiply by 1? What you had before. You haven't really changed anything. You put a tuxedo on the chimp. It's still chimp. That's the idea. So let me erase that because I don't need that at the moment. Whoops, that's highlighting, not erasing. So let's see here. Then we had 1,000 meters will be in a kilometer. And let's see, it's per million years, so that would be 10 to the 6 years per, I guess, million year. We do that. So if you multiply all of that out, so you have 4 million, because 4 times 10 to the 6 would be 4 million, divided by 100,000. So you have 10 to the 6 divided by 10 to the 4th, or 10 to the 5th, rather. It's really what you have. So you have, I'll write this out. You have 4 times 10 to the 6th in the top. Okay, let's kill our, so centimeters drop, years drop, meters drop, and you're left with your kilometers per mega year. So we have the right units. That's what the question was asking for. So you have 4 times 10 to the 6 kilometers over, that's 10 to the 5th. You see how it's 1, 2, 3, 4, 5, 10 to the 5th, 10 to the 5th mega years. And that's why you just get 40. 40 kilometers per mega year. So a million years from now, pretty much all the continents will have moved 40 kilometers. The shorelines will be different. And what that'll do on the inside of those continents, who knows? Find out in a million years what's going to go in. So this is we started the problem with a useful, easy to perceive, I can imagine 4 centimeters per year. That's really slow. That's why I don't notice big changes in the continents in my lifetime. But then if you wanted to predict with this really simple data point that is pretty much, it's pretty accurate, about 4 centimeters per year, we've been measuring it for decades, what will happen in a million years? Well, 40 kilometers later. All right, that's big. And in 10 million years or a billion years, you know, we can predict, assuming things go like they're going now, which we have good reasons to think that it'll stay that way. So on our way to, we started with a useful data point and we ended with a useful data point, and in the middle, we seemed to do some stuff that didn't seem to really be that helpful. It wasn't a unit that was useful to us. Okay, and that changes according to whatever your domain of inquiry is. All right, so any questions on that problem? All right, good. Moving on. Suppose your bathroom scale reads your mass as 65 kilograms with a 3% uncertainty. So in our textbook, which I want you to read through, and you'll need to read through because the concept quiz and the homework will ask you to do uncertainty calculations. So we're going to start doing that now, and then these will move forward into various lab events that we're doing. All right. So let's talk about this. What would it mean, percent uncertainty? So just so you know, and this comes straight out of your book, this little funny squiggly thing, the uncertainty, we also use, this looks like a partial derivative in calculus, but we're not calculus. The uncertainty of the mass. So this little squiggly d, and it could be the uncertainty of mass, could be uncertainty of speed, whatever letter goes with whatever it is we're talking about. This time we're talking about the mass, what you read on a scale. And so if my uncertainty of mass is 3%, meaning 3% out of 100% would be one way to talk about that. 3% is also just 0.03, right? Okay, so there's what a textbook will tell you, and then there's, well, why didn't you just say it the easy way? Okay, sometimes the textbook says it as easy as it can be said. This is not one of those times. Okay, right? Isn't that a kind of an not an entirely useful number of symbols to just say 3%. Okay, why am I doing this? One, to confuse and outrage you. I need to do some of that. I'm paid to do that. Just kidding. But it's the jargon, and you'll read about it in the book. And there are times where the symbolic jargon is a useful tool to us. We'll get to that. So just sort of, this is just a warning. Danger, Will Robinson. Okay, so the uncertainty. So this 3%, okay, of 65 kilograms. Okay, well, 3% of that, basically 2 kilograms. So the uncertainty of this bathroom scale actually ends up being, let's see, I think it's 2.2 pounds per kilogram. I think that's right. So that's off. That's a bad scale. I'm taking that one back. All right. So it's an uncertainty measure. There's probably no scale that's really that bad. They probably don't sell them that bad. You abuse them and they become that bad. So it's simple. That's all there is. The uncertainty in the measurement is 2 kilograms. All right. Every one of you will eventually have to take statistics. Often the uncertainty of a measurement will be at this thing called the standard deviation. Like, it's 100 pounds plus or minus 2. That's that uncertainty measurement. What range is, how precise is this measure, this data? So we try to get our uncertainty really, really small. Okay. Sometimes we can't though, because our techniques for measuring aren't good enough yet. All right. Moving on. Is this format helpful? It's clear. I should have sent it out in email. At least you could have printed it off if you wanted to do that. But you could also go back and by the way, the problem numbers are right out of your book. So you could go back and reference that directly if you have a version of the book that's numbered, which isn't the HTML version, the PDF, Kindle, print. All right. Good quality measuring tape can be off by half a centimeter over a distance of 20 meters. So 1 meter is roughly a yard. So half a centimeter per 20 yards, if you will. All right. What is its percent uncertainty? All right. Here's a new formula straight out of your book. So the percent uncertainty, that's UNC, of length, we're dealing with length here, will be this weird formula. So the percent uncertainty of the length is the uncertainty of the length per unit length times 100% or times 1. Okay? And so, again, I think sometimes looking at that formula and then understanding what it's trying to tell you to do is, well, we'll get at that. So how's this going to work out for us? Good question. Glad you asked. So what do I have? I have half a centimeter per 20 meters. That's the translation. So this and this are the same thing. The uncertainty in the length per unit length would be, just like the problem said, half a centimeter per 20 meters. Almost every quantity cannot be described. There is no quantity that can be described in terms of itself. Every quantity is always described in terms of another quantity. Think about that. But don't stay up too late, all right? Unless you don't have classes tomorrow. All right. And so guess what this means, though? Centimeters per meter, I need 1 unit of length, not 2 units of length, all right? So what we're going to do is let's multiply this by let's see, 1 meter per 100 centimeters. And all my units drop out. That should make sense because length is length. One length per another length shouldn't leave me with anything but a number. The only way I could do that is if I get them to be the same, if I convert them to the same unit. And so this times 100%, and what do I get? I get 2.5 times 10 to the minus 2%. It's a strange kind of percentage because that would be 0.025%, which isn't 2.5%. It's way less than 2.5%. It's a fraction of 1%. All right, so that's one of the reasons why the formula, using it in some way is helpful, because you won't make the mistake of converting that to a decimal and then that decimal to a percent. So this is where you're going to make a mistake on the homework, okay? Because so far we've done arithmetic, all right? You'll get hung up on these little things. It's fine. You know, your homework is your homework is mostly a completion grade, by the way. So if you could conceivably get every problem technically wrong, provided that you were at least in the ballpark. Well, maybe down on the field, okay? If you're off at the Haagen-Dazs stand and your homework, yeah, I'm going to jockey points. But if you're on the field, if you're out, you actually used the right formula and maybe did some silly arithmetic error, I'm going to go fine, okay? So I'm mostly looking for completion in the homework. The quiz, not so much. That's more of a little test, all right? But the quiz comes after the homework. So we work it out, figure out what's wrong, then have the test in the week that follows. So homework quizzes are always the week that follows, all right? Usually on Monday, first thing, okay? All right, so that's the end of that one. A speedometer has a 5% uncertainty. What is the range of possible speeds when it reads 90 kilometers per hour? I know we're in America, and we use miles per hour in America, all right? But this is a science course, and we're going to do metric most of the time, says Professor Mater. All right, so let's see here. Well, what is the range of speeds when you have this uncertainty? Well, strange squiggly uncertainty of speed is 5%. I'm going to go ahead and do kind of the textbook approach. That way you've got something to look back on when you look at the textbook. All right. Times the 90 kilometers per hour. You can do kph. Works as well. And what do you get when you do that? Well, it looks like 4.5 kilometers per hour. That's the uncertainty of the speed, give or take. 90 kilometers an hour, you give or take 4.5 kilometers per hour. All right. So if you have a digital speedometer, it's probably not that bad. Analog speedometer, still probably not that bad, but on its way to it. All right. So a lot of new cars have this. So the range would be 90 kilometers per hour plus or minus 4.5 kilometers per hour. And so if you wanted to give an interval, you would just subtract 4.5 from 90. That would be your low end of your interval. So that would be 85.5 kilometers per hour on one end of the interval and 94.5 kilometers per hour on the other end of the interval. So, you know, if we were to have our speed interval, you know, it'd go 85.5 to 94.5. So just to kind of give it a intermediate algebra interpretation. That stuff wasn't totally useless, all right, when you were taking your math courses. All right, that's it. That's the range of speeds. If we wanted to convert it to miles per hour, we could do that. So let's say it wasn't asked in this problem, but I'm going to do it anyways. So let's see, kph to miles per hour. Be great if we were in the car. We could just look at it, but we're not in the car. So if I have, let's just do this low end, 85.5 kilometers per hour, okay, and a kilometer is 0.6214 miles. So there we go, miles per hour. So I'm going to have 53.1 miles per hour. Nice thing here, on your homework, I need you to show the work. Guess what you can do? If you go to Google search line and say, 40 mph2, before you're done typing, it'll say to kph or some meters per second. So you can just hit it, and it'll tell you what the right answer is. So the Google search line can convert most anything. In fact, you do one, it gives you a whole panel, and you can pick what units you this to that. So there's a lot of easy ways to know that you have the right answer. If you have a graphing calculator, most of them will do unit conversion as well. All right. So don't just state an answer, but you can, most of these problems, you could know what the right answer is before you're done. You just need to make sure your work demonstrates it. All right. So I'm a fan of using the technology. Because this isn't supposed to be a math course. We will use math, but I'm trusting that you know that math. So if you want to use calculators to finish the work, fine, do it. But set it up, press the button, move. All right, significant figures. Anybody had significant figures in another course where they talked about that and made you do it? So your book has a section on significant digits. The key idea, the easy part of this is if the zeros in between non-zeros are always significant. That almost always tells you how to count significant digits. Okay, and then there's some gray area around the edges, okay, that we'll get to soon enough. All right, so how many significant digits are in these calculations? So let's see here. How many significant digits are in this number? Just given the rule I gave. First, number one rule, if it's not a zero, it's significant. If the zero is between non-zeros, it's significant. So how many significant digits are in that number? 4, right? All of the non-zeros, there's 3 of them, and then a zero in between the non-zeros. They're all significant. What about this number? Is a zero at the end of a number significant? Yeah, it is here because it's saying it's exactly, which is impossible, but sometimes we assume that it's that. All right. So what about these other two numbers? Do they have the same number of significant digits? Is there a smaller number of significant digits? No. So one of the other, almost all of the rules now in significant digits is that when you do a computation, whatever input has the least number of significant digits, that's the number of significant digits you report your answer to, because it's essentially the weakest link in the chain. All right? Those numbers are the least precise. Therefore, any computation, it wouldn't matter if every other number had 1,000,000 digits of precision. They wouldn't help me because I'm limited by the precision of the least number of significant digits. So when you read through those significant digits rules, and there's examples in your book where they do the same sort of thing, pay attention to that. Okay, but most of the time, non-zeros are significant, zeros between non-zeros, zeros at the end. And when you do a computation, whatever the least number of significant digits is, that's what you report your answer to. So when you take a quiz and ask the question, there'll be one answer in the computation, and you'd better round it to that number of digits in the number, which is not the same as the number of decimal places necessarily. Yes. Right, right. So you always want to carry all the digits forward. Don't do a computation, round it, then use that in the next computation. Always save the rounding for the answer. Carry all the digits, all the bags, all the way through the computation. And then at the end, do the rounding. Otherwise, you propagate rounding error. Okay? You're not accounting for all the precision. All right? So good question. So 3. The answer here is there are 3 significant digits. This next one, hopefully this isn't too mind-numbing, but how many digits? 3. And I'm squaring it. So again, it's going to be 3, number of digits in that. Now, one of the rules, when you have scientific notation, that don't have nothing to do with the significant digits. Your power of 10 multiplier, not part of the significant digits. Just what you write, the multiplier. And if you end in 0, you're saying that that 0 is significant. Okay? The zeros that aren't significant are the ones that are between the decimal point and the first non-zero. Those aren't significant digits. Why? Because basically they're a power of 10. If you converted it to scientific notation, in fact, your book will tell you that. Decimal numbers, convert them to scientific notation, and then you count significant digits. Or just look at it and ignore the zeros between the decimal point and the first non-zero. But zeros between the remaining non-zeros, those will be significant in a decimal number. So, all right. So we got, what do I have here? I have 3 there and 4 there. So guess what? 3. All 3 of these are 3 significant digits. All right. So there's stuff to read about that. I gave you the overview. Read about it. Concept quiz will ask you a question or two about significant digits. So when are you going to use it? Every homework problem, every homework quiz problem, every celebration of knowledge problem where you compute significant digits. We'll use significant digits all the way through the course. Anytime you do a computation in this course, do the significant digit dance. And by the end of this course, you will know significant digits backwards and forwards. And then you'll go out to a job, and either they'll pay attention to that or they won't. All right? A lot of the time, the work gets so routine that you just always know it's 3 decimal places. All right? And sometimes the significant digits don't really matter that much in this particular application or that one. It varies. But if you know significant digits, you can handle any twist out there in the real world. All right? Sometimes it matters, sometimes it doesn't. We'll pretend it matters. All right? Significant digits matters. A t-shirt or something. Marathon runner. So uncertainty, a bunch of uncertainty stuff here. So completes this 42.188 kilometer course. Okay, somebody really got their tape measure out. In 2 hours, 30 minutes, 12 seconds. There is an uncertainty of 25 meters in the distance traveled and an uncertainty of 1 second in the elapsed time. So 2 uncertainties to deal with. Calculate the percent uncertainty in the distance, calculate the uncertainty in the elapsed time. Simple calculations. So let's get at it here. So part A, so percent uncertainty in the distance will be 25 meters per 42.188 kilometers, which means I have a kilometer per 1,000 meters, all right, times 100%, and that's going to give me 0.0593%. Okay, now that's my unsignificant digitized answer, right? How many significant digits do I have in this calculation? What's the least number of significant digits? So I have, for distance, I have this number and this number. What's the least number of significant digits? 2, right? So that means when I report my percentage, I can't give 3. Right now, 0.0593% is 3 significant digits. So what would this be in 2 significant digits? Oops. Lost my pen here. What I would do is I would just drop that 3. 0.059%. That's 2 significant digits. The zeros between the decimal point and the first non-zero in a decimal part of the number aren't significant. So at this point, I've actually demonstrated all of the significant digits rules. I just didn't put them in a boring list like your textbook has. You need to read that boring list, internalize it, name children after it, get a t-shirt, because you need to follow those rules. Maybe print it, write it out, make your own version of it. Okay? I'll provide formula sheets, but I won't give you those rules. You need to learn that rule. All right? So there we go, percent uncertainty and distance. Part B, percent uncertainty in time. I'll use T for time. So I have 1 second per 9,012 seconds. Now, where did I get that from? Do the math. Convert 2 hours to seconds. Convert 30 minutes to seconds. Add those seconds to the 12 seconds, and you have 9,012 seconds. All right, so I didn't show the conversion, but just take my word for it. Press tab. We've done enough busy work. I don't need to make you do all of the busy work, okay? But in a problem like this, you would need to do that. So what would be fine with me is if you could just write for this, you could just go convert it on your calculator or something and write in the number of seconds. Or you could write it all out. Whatever floats your boat. I don't care. All right, so you don't, stuff like that isn't that big a deal. So times the 100%, it's already got the units taken away, and so what do we get? We get 0.0111 if you were doing this on a calculator. And really, we have 1 significant digit. 1 second is our significant digit. And so we would have to write 0.01% as the uncertainty in time. Okay. However, this is where it gets a little challenging because if you think about it, is it possible to measure exactly 1 second? You're lucky if your stopwatch stops at 1 second. Is it possible to measure exactly 12 gallons of gas? No, it's not. You know what exact numbers refer to? There's exactly 4 tires on my car. Exactly 2 eyes in my head. So if something's countable, you can have an exact number of it. But if anything requires, a volume or a length measure, there are no exact measurements. There are really super duper precise and accurate enough that we could assume that I have exactly 1 meter or exactly 1 second. But in reality, nah, you can't really do that. But you can get so close that you don't care. How many had calculus? It was like everybody, right? Limit process? Okay, so it's sort of like Zeno's paradox. Pause this right here. Well, I'll let it run, even though nothing's happening on the screen. So anybody heard of Zeno's paradox? Good. I'll tell you about Zeno's paradox. Zeno was this Greek dude, philosopher, Greek philosopher back in the days, all right? And he had this paradox, and I think he knew better, but it was about they would sit around and think in between partying. Seriously, that's what they did. And he said, all right, if you have a trip, and every leg of the trip, you're only allowed to go halfway. So if I'm going from here to the wall on day one, I go halfway, stop at the Hilton, order some room service, watch some HGTV, whatever. Next day, get up, go halfway. Next day, go halfway. And if I keep having to go halfway, technically speaking, I never really get to that destination because I'm always subdividing the remaining length interval in half. Even though I could, touch the wall, just think of a line, like a number line. And so he's like, motion is impossible because that was his paradox, all right? And so the idea is that you can't exactly get there, but the limit process, we know if I could keep dividing it down to eventually I have such an infinitesimally small division, I'm essentially there. That's the idea of the limit in calculus, all right? Whether or not that was clear in calculus or not, I don't know. Depends on the teacher, but physically speaking, that's why we take it as an answer, all right? We pretend that it's exact, even though really we have nothing that is that precise. So, percent uncertainty, distance, and time. Well, let's continue the problem. I did A and B on one slide because I didn't think I'd have room for C and D, but I ended up having it. So now let's do C and D. What's the average uncertainty or average speed in meters per second? And then what's the uncertainty in the average speed? So we haven't studied speed yet, but I think you know that speed comes in units of length per unit in time, right? You've driven a car, you know what speed is. I'm not going to pretend you don't know what speed is. You may not understand it fully, but you know what it is. So part C. Oops. Average speed. Will be the distance, 42.188 kilometers, the time that it took, 9,012 seconds. Okay, and so if I have 1,000 meters per kilometer, then I get meters per second. If you do that math, you come up with 4.681 meters per second. That's believable on a runner. That's 12 yards, 15 yards. So they're cooking along at a pretty good pace. All right. Average speed, sometimes faster, sometimes slower. All right, over this time. So we did the computation. Yay! What is the uncertainty in the average speed? So the percent uncertainty in speed will be the percent uncertainty in distance plus the percent uncertainty in time. Now, here I am bringing out a new rule that you will read about in your textbook. And so there are times where we add uncertainties, and there are times where we multiply or divide uncertainties. Okay? And that will become clearer as we move forward. But I have two uncertainties and a this for that sort of thing. So when you have these, ultimately what it's going to boil down to, unless I need more coffee today, is when you're doing computations about the same unit, then you'll be multiplying them. And if you are doing them about different units, you're going to be adding them. Because if I have an uncertainty in this measure and an uncertainty in this other measure, that means my overall uncertainty has to add up in that regard. And so we had 0.0. Now, if you remember, so I'm given the full precision, not the significance here. And the uncertainty in time I'm sorry, the distance was, I'm like not reading my own notes here well enough. The uncertainty in distance was the 0593 number. And the uncertainty in time was the 0.011. So I'm going back to the full precision, okay? And you would notice a slight difference if you took the rounded versions and added them. You might be wrong, all right? But so you go back to the full digit precision, and this gets you to the 0.0704%. But again, given the number of significant digits as just one, then you get 0.07% for uncertainty and speed. So idea here, I'm giving you some examples. There's some reading to be done about this. What I want to do is early in this week, get the examples out to you. Give some explanation. I've given you most of what you'd find in the book. Usually what happens for most folks is if you get some sort of explanation and then you go read something, at least you're prepared to read it, all right? Whereas sometimes just reading it cold is, what is that? You know. All right, so that's that problem. How many heartbeats are there in a lifetime? Seems like a strange question, and what data would I pull on to do this? Sometimes I'll ask questions that will require you to make assumptions. That's part of the puzzle of doing science. Just make an assumption, justify the assumption, see where the assumption takes you. Does the assumption correspond to reality or your perceptions thereof? Okay. Here in a few weeks, I'll give you problem statements that don't even ask a question. You're going to have to start modeling it and seeing what you can generate with the information you have. It's another, because trust me, when you get out to your real job, it's not going to hand you a workbook, all right, with questions. You're going to have to start with what you have and go generate new information and see what that information tells you. That's the way it really works in the sciences. Anyways, how many heartbeats are there in a lifetime? Well, one lifetime, pretend that that's a unit, and I'm going to convert it to heartbeats. Well, there's roughly 1 billion seconds in a lifetime. In fact, right out of your, I take that back. This came out of your book. In half a lifetime, there's roughly 1 billion seconds. Why is this? Well, anybody have a calculator out that they could use, your phone or something like that? If memory serves me well, there's like 30 some million seconds in a year. So there's 3,600 seconds in an hour. So 3,600 times 24 hours in a day. So 3,600 times 24 times 365. Isn't that like 35 million or something? 30 some million. So multiply that times 100. Go for a long lifetime. What's the power of 10? So just throw 35 million times that. Well, 35 times 10 to the 6 times 10 to the 2. So it's 35 times 10 to the 8. And 35 is 3.5 times 10. So you have 3 times 10 to the 9th. You get a power of 10 equal to 9. Okay, and 3.5 of them or something like that, or 3 of them. So half a lifetime or a whole, I could write just 1 10 to 9, 1 billion seconds per lifetime. Okay, so it's an assumption. All right, that's all that really matters. But I'm pretty sure this one comes, there's like a table in your book of number of seconds in a lifetime, or in like the age of the universe of roughly 14 billion years, that's 10 to the 17 seconds. All right, so weird stuff. And let's see, you pretty much, how many heartbeats per second do we have? Spelling, all right, beat. I would say that we usually have 1 heartbeat per second. Okay. Resting heart rate for most people is roughly 60. If you're an athlete, it's 50. Right? If you're sick, it's 80, right? Or excited, or holding your breath, or something like that. So 1 heartbeat per second. So let's see here. Lifetime drops, second drops. So how many heartbeats in a lifetime? Well, 1 over half is 2, correct? So 2 times 10 to the 9, create a new unit, HB for heartbeats. Probably refers to something else. So 2 billion heartbeats in a lifetime. Okay, so it's an assumption. And if somebody were to do more precise calculations, like, all right, I'm going to look up the average lifespan. It's probably close to 80 years, 78, 80 years, depending on if you're male or female. And then you could really drill into, what's the average resting heart rate? You know what would happen? You'd probably get the same order of magnitude number. You would still be in some single digit number of billions of heartbeats. And when you're talking about billions, if I had $1 billion or $10 billion, I really wouldn't care. I could live with $1 billion, just 1 billion. I could deal with that. I'd be okay. I'd get over it. All right. So that problem is largely about assumptions and seeing what they can deliver. All right. All right. I think this is the last one. Pretty sure. Yes. Right on time. How many times longer than the mean life of an extremely unstable atomic nucleus is the lifetime of a human? Okay. So basically, let me give you a data point here. The mean life of an extremely unstable atomic nucleus, that will be about, what is it? Oh, I put it down there already. 10 to the minus 22 seconds. So 10 to the minus 22. So 10 to the minus 11, or 10 to the 11th is a billion, 100 billion. Okay. Square that, multiply by itself, it's even smaller. So mean lifetime of an unstable nucleus is an insanely small amount of time. 100 billionth of 100 billionth of a second. That's what 10 to the minus 22 refers to. So we just make a ratio here. So the time of a heartbeat, or lifetime of a human in heartbeats, that's why we did this previous problem, to the time of an unstable nucleus, there. So we had 2 times 10 to the 9 seconds, because remember when we were assuming 1 heartbeat per second. This is a tough problem because there's no formula here. This is all proportional reasoning. Okay, so if you're, what's the formula? What's the formula? There's no formula here. There's only thinking. So you may have to go back and listen to this and see how we came to these conclusions. Okay, so the question is, how many times longer than the mean life of an extremely unstable atomic nucleus is the lifetime of a human? Well, I'm told that the time frame for an unstable nucleus is this 10 to the minus 22 seconds. So that's constraining the way I even frame the problem. Okay? I just did a problem where we figured out that one of the factoids was that, if there's 1 heartbeat per second, I'm going to have 2 billion heartbeats, which means I'm going to have 2 billion seconds. Okay, and so I'm taking this fact that I derived from some other consideration. If I didn't know that, then I would have to have done this calculation some other way. And I'd have something on the same order of magnitude, billions, single digit billions, but it would be fundamentally, it would not be different. So I'm just pulling forward previously known data, all right? And so how much longer is the mean life of the nucleus versus a lifetime of the human here? And so you end up getting 2 times 10 to the 31 times. So humans have a lifespan that is 10 to the 31 times longer than this unstable nucleus. So this is not a useful piece of information. Admitted, right? So what? Why are you making me do this? Because we are going to do other calculations where you have to deploy the same reasoning, but we're not to that content yet. Okay, we're not dealing with energy or momentum yet. And in those contexts, we will want to compare numbers and come up with this is this many times bigger or smaller than that. Then it will be useful to do that calculation. But there's no formula for that. There's just thinking it through proportionally. So this is our first shot at thinking it through with 2 known quantities. How much bigger is this than the other? That's all that's about. So a lot of times we have a standard formula that you could look up from a table. And then times we just have to think it through proportionally. That's the reason this problem exists. As much as I can, I try to give you the reason why we're doing what we're doing. And sometimes it's obvious why we're doing it that way. And then other times it just looks like busy work. Or it's imponderable because there's no formula and you desperately want a formula. So I try to warn you. If I don't, ask, is this one of those, things? And then I'll let you know.